Today, we're going to be looking at how the Serial Wombat Watchdog function can increase the reliability of systems. In this case, we have an Arduino Uno that's attached to the Serial Wombat. It's driving it via I2C, and the Serial Wombat's pin number 2 is attached to the reset pin on the Arduino Uno. This allows the Wombat to reset the Arduino. Looking at our code, we've already installed the library for Serial Wombat. If you don't know how to do that, watch another video on it that's in this channel. We declare a Serial Wombat, then declare a Serial Wombat Watchdog that's part of that Serial Wombat. We do an I2C initialization, making sure that we've chosen the proper I2C address for the Wombat that we want to talk to. We do a begin call. This begin call is more complicated than some. We tell it we want it to be on pin 2. During normal operations, we want the pin to be an input, effectively disconnected. During a reset case, we want the pin to go low. We want the countdown timer to be 10,000 milliseconds. And we have the option of making the Serial Wombat also reset itself after the timer expires. We're not going to do that here, so we're going to set this value to false. We'll also set up our serial so we can monitor what's going on via the serial terminal. Let's create a flawed function that will lock up our Arduino. We're going to create a division function that does division by repeated subtraction. But there's a flaw in it. A number that we should have declared as an int, we declared as an unsigned int. So effectively, it will roll over if it gets negative numbers. For instance, if you take 2 and try to subtract 7 from it, you would lose the 2. Then the value would go to 256, from which you would subtract 5, and the net value of 2 minus 7 is 251. So this function is going to work poorly for cases where there are not perfect no remainder division. In our main loop, we're going to divide the number 60 by a series of incrementing numbers. 60 divided by 1, divided by 2, divided by 3. We'll do one division every second. Each second, we will also tell the Serial Wombat, reset your Watchdog timer back to 10,000 milliseconds. Everything is fine here, situation normal. Things are running well. We don't need you to reset us. We are on track. So we'll go through here, and this loop will continue. If we had perfect software, it would continue indefinitely. But we know that we have a flawed function here that will lock up the Arduino. Let's take a look at what that looks like. Here we can see the code executing. It goes through setup, then starts iterating through factors of 60. When it gets up to 7, we start seeing the flaws. When we get to 8, we can see that it stops during the calculation of the division. At this point, we waited. It was 10 seconds after this division attempt. Then we got a reset. We went back to the setup routine at the top and ran that. We'll see it happen again. We can see this process happening if we watch on a logic analyzer. The bottom channel is the reset pin. The top 2 channels are the I2C traffic going into the Serial Wombat. As we see, after each of the divisions, we send an update command to the Serial Wombat that says, please reset your timer. However, after it reaches the 8 here, those pulses stop because the Arduino is effectively locked up. Then we see the Serial Wombat do a reset and additional setup commands, then iteration again through the division. If we take a look at the duration, we see that it's quite nearly exactly 10 seconds from the time of the last transmission until the Serial Wombat pulls the reset pin, after which there's a couple of seconds worth of boot up time for the Arduino. Then we start iterating through, doing the divisions and resetting the Serial Wombat Watchdog. We know that the Arduino also has some Watchdog libraries available that can cause internal resets. Like a lot of the Arduino functions, each library is only compatible with certain Arduinos because the Watchdog tends to be hardware dependent. In the case of the Arduino Uno, the most popular Watchdog has a maximum expiration time of 4 seconds. So one reason you might want to use the Serial Wombat is that it has a period that can reach all the way up to 65,000 milliseconds or 65 seconds, a little over a minute. Another use for the Serial Wombat Watchdog is to use it as a pulse that will automatically shut off. Imagine for a moment that we have a motor that's being driven by the Serial Wombat, and something bad could happen if that motor continues running in the event that the Serial Wombat loses connection with the Arduino, or that the Arduino fails to send a command to shut it back off when it's finished. We can use the Watchdog output as a digital input-output that will shut off itself if not commanded to stay on periodically. In this case, we would say we want this pin to be low as a reset result, but high during the normal operation. Then when the Arduino was actually finished with this, we would reconfigure this pin back to a low output to shut the motor off. But in the event that the I2C traffic stopped or the Arduino locked up, you've already set a timer on the Serial Wombat, which says, if I don't talk to you for 2 seconds, shut off the motor automatically. If you have questions about how to use the Serial Wombat's Watchdog, or if you've successfully used the Watchdog as part of a design, please leave me a comment in the comments section below. The Serial Wombat open source project was created by Broadwell Consulting Inc. Broadwell Consulting Inc. provides help developing medical devices with a focus on developing embedded firmware, which is compliant with IEC 62304, ISO 14971, and ISO 13485, as well as remediation assistance for products already in production. For more information, contact John at Broadwell Consulting. Support requests for Serial Wombat should be sent to help@serialwombat.com and will be answered on an as-available basis. Questions sent to John at Broadwell Consulting about the Serial Wombat will not be returned.